Myself, Dr. Somit De, teacher in charge and assistant professor of mathematics section under Department of Basic Science and Humanities, Asansol Engineering College. This is lecture number 1 under module number 2, paper name Mathematics 1A, paper code BSM-101. This subject belongs to Computer Science and IT BTech first semester. Topic is mean value theorem. MVT means mean value theorem, belongs to calculus part. Rolle's theorem, the statement are important. If let fx be a function defined on the closed interval AB, satisfying the following conditions: fx is continuous in closed interval AB, and number 2, fx is derivable, means differentiable, in the open interval AB, and number 3, fa is equals to fb, then there exists at least one value c where a less than c less than b, such that f dash c is equals to 0. So this is the statement of Rolle's theorem. So there are 3 statements you have. There are 3 conditions you have. Number 1, your function is continuous in the closed interval, and fx is derivable or differentiable in the open interval, and third, most important, that is fa is equals to fb. If all these 3 conditions are satisfied by any function, then we can find at least one value of c, that is c belongs to ab, that is in between ab, such that f dash c is equals to 0. Okay, so this is the statement of Rolle's theorem. Geometrical interpretation of Rolle's theorem. This is also very, very important. Since the function fx is continuous on closed interval AB and is derivable on the open interval AB, the continuous curve has a unique tangent at each point on it, except at the end point A and B. From the figure it is clear. The third condition implies that the curve y is equals to fx has the same ordinate at A, at the point A and B. Fb is equals to fa, means this value, this is A, and this is fa, this is B, this is fb. If fa is equals to fb from the third condition, so ordinate should be same according to the condition. The slope of the tangent at c, x equals to c, is f dash c is equals to tan theta. Okay, tan theta. Now if all the conditions satisfied, number 1, fx is continuous in closed interval, this one, fx is derivable in open interval, this one, and last, that is fa is equals to fb, satisfy all 3 conditions, then f dash c is equals to 0, which implies that is f dash c is equals to 0 means tan theta is equals to 0, which implies that theta is must be 0. It means the tangent to the curve y is equals to fx at x equals to c is parallel to the x-axis. This is vital information or vital significance. So that means geometric interpretation is that the tangent to the curve y is equals to fx at x equals to c is parallel to x-axis based on Rolle's theorem, because f dash c is equals to 0. If f dash c is equals to 0 means tan theta is equals to 0. Tan theta is equals to 0 means theta is equals to 0 degree. Okay, so this is the geometrical interpretation of Rolle's theorem. Now try to understand with some example what type of question you can see from here. Try to understand, very easy. Now verification part. Question: verify Rolle's theorem for the function fx equals to x square minus 5x plus 6 in a less or equals to x less or equals to 4. So from the given question, it is just you have to check whether all three conditions of Rolle's theorem are satisfied or not by the function fx or not. Okay, clear? So from it is clear that the given function fx, x square minus 5x plus 6, 1 less or equals to x, this is a defined part. This is question number 1. Since fx is a polynomial function, so it is continuous on closed interval 1 less or equals to x less or equals to 4, because there is this polynomial, so that means it's a continuous. And this function fx is also differentiable in x less or less than x less or equals less than y. Then why without any, suppose you have a question in your mind, sir, without, yes, suppose you differentiate this, what is your f dash x? F dash x is 2x minus 5. Whether it is a discontinuity, do you have anyone? No. So from here it is clear, just to remember this, polynomial function always continuous, always. Okay, similarly differentiable also. So from here your function is defined within 1 to 4. Just to substitute the value x 1 to 4, any value to the function, just to check, can you identify any undefined case? No. So that's why your function is continuous within the closed interval. And if I differentiable, it's not it's differentiable throughout. Just to differentiate f dash x equals to 2x minus 5, now you substitute any point between 1 and 2, any value of x between 1 and 4, any, you will get some value. That is no undefined case. So that's why your function is differentiable in 1 less than x less than 4. Now you check f1 means 1 square minus 5 plus 6. What is the value? 1 plus 6, 7, minus 5, 2. You have this. And f2 is equals to f2 is equals to 4 minus 10 plus 6, sorry, 4. f4 is equals to 16 minus 20 plus 6, 16 plus 6, that is 22, minus 20, that is 22. So from here it is clear, fa is equals to fb. So thus all conditions of Rolle's theorem are satisfied. So that means number 1, your function is continuous in 1 less or equals to x less or equals to b, that is a closed interval, and the function is differentiable in open interval 1 less than x less than 4. And third condition, fa is equals to fb. So here a is equals to 1 and b is equals to 2. So fa is equals to 2. If you substitute here, you can find similarly f2, f4 is equals to 2. So fa is equals to fb. So thus all conditions of Rolle's theorem are satisfied. Clear? Clear? I think you have a question in your mind, from where you have this. Very simple. Just you check if f1 is equals to 1 square minus 5 plus 1 square minus 5 plus 6 is equals to 7 minus 2. Now f4 is equals to that is 16 minus 20 plus 6 is equals to 2. So for this reason, clear? I think you have a question in your mind, from where you have these 2. So this is the logic behind this. f1 is equals to 2, f2 is equals to 2. I substitute here. Okay. Okay. So therefore, thus all conditions of Rolle's theorem are satisfied. Therefore, according to Rolle's theorem, there are at least one C belongs to 1 and 4. which satisfy f dash c is equals to 0. Now what is your f dash s? F dash x equals to 2x minus 5, and f dash c is equals to 0 gives you 2c minus 5 equal to 0. That is c is equals to 5 by 2. 5 by 2 is 2.5. 2.5 belongs to 1 and 4. Okay, since we found the one value of c, that is 5 by 2 belongs to this, such that f dash c equals to 0. So we conclude that the Rolle's theorem is satisfied for the function fx equals to x square minus 5x plus 6 in 1 less or equals to x less or equals to 4. So this type of question you can see in your question paper. Next question. So last one is second order type. Now question number 2. Verify Rolle's theorem for the function x cube minus 6x square plus 11x minus 6 in 1 less or equals to x less or equals to 3. So number 1 here, fx is continuous because it's a polynomial function, is continuous in closed interval 1, 2, and f dash x, what is your f dash x? Just differentiate this. 3x square minus 12x plus 11 exists in open interval ab, that means your function is differentiable, and f1 is equals to f0, f1 is equals to f3. Same way, if you substitute one value, we can find okay, one value we can find that you can check. Okay, suppose you want to check f1 is equals to 1 minus 6 plus 11 minus 6 is equals to how much? 0. Now f3 is equals to 27 minus 54 plus 33 minus 6. Please check how much. That is 60 minus 60, 0. Okay, so from here it is clear that the fa is equals to fb. So that means hence all the conditions of Rolle's theorem are satisfied. Therefore there exists a point c in between a1 and 3 such that f dash c equals to 0. Now f dash c means what is your f dash? F dash is equals to 0, that is 3c square minus 12c plus 11 equals to 0 by using Siddharth formula. Can you recall your Siddharth formula? What is your Siddharth formula? What is your Siddharth formula? Ax square plus bx plus c is equals to 0. If you have, then x is equals to minus b plus minus root under b square minus 4 ac by 2a. This is your Siddharth formula. Okay, so using it we can find that is c is equals to 12 plus minus root under b square 144 minus 132 using this formula. So a is equals to 3, b is equals to minus 12, c is equals to 11. So 12 plus minus root under 12 by 6. After simplification you have 2 plus minus root 3 by 3, that is 2 plus minus, so just calculate this representation mistake, it's 6 by 6 by this. So that means you have this is typing mistake. It should be 2 plus minus 1 by root 3. So already you know root 3 value is 1.732. If I divide by this 0 point something, so 2 plus 0 point something, 2 minus 0 point something. Ultimately from here it is clear your c value lies in between 1 and 3. So hence verified Euler's theorem. Next question number 3. Same, verify Rolle's theorem for the function fx equals to x root under 4 minus x square in 0 less or equals to x less or equals to 2. Here the given function fx is equals to x square root under 4 minus x square is continuous. There is no break, so that's why your function is continuous in 0, 2, that is closed interval. And since f dash x equals to, just you divide uv formula, u x 4 minus root square plus x into minus 2x by this, that is ultimately you have 4 minus 2x square by square root under 4 minus x square. So that means that your function is differentiable on 0, 2. Further, f0 is equals to 0, f2 is equals to 0. Already I discussed in my last two consecutive question. So you can substitute same way. If you put x equals to 0, so from here it is clear the value will be 0. Okay, it should be now f0 is equals to f0. If you substitute here 0 into something means 0. Okay, from a f0 is equals to 0, that is 0 when you put is equals to this f0 is equals to 0, and f0 is equals to 0 when you put x is equals to 2 to the function, that is 4 minus 4 0. So ultimately this third conditions of Rolle's theorem is also satisfied. So thus fx satisfies all conditions of Rolle's theorem. Now f dash c, if all Rolle's theorem are satisfied, all conditions of Rolle's theorem are satisfied, then is satisfied, then f dash c is equals to 0 gives you, that is 4 minus 2c square by square root under 4 minus c square equals to 0. From where you can get 4 minus 2c square equals to 0, that is c is equals to 2, that gives you c plus minus root 2. So what is the value? Your value is 0 to 2. So that means minus root 2 is not belongs to this range. So okay, since root 2 belongs to this, so Rolle's theorem is verified. So hence Rolle's theorem is verified for the function this. Clear? Very easy question you can see from here. First you have to check whether your function is continuous or not within closed interval. Then you check whether your function is differentiable or not, is closed open interval. Then you check f a is equals to fb, yes or no. If yes, then you have to find f dash c equals to 0. So you have to check whether your c value, that is c value belongs to this region or not, belongs to this interval or not. It should be an open interval. So there exists two value of c, that is plus minus root 2 and plus minus. So here your plus root 2 belongs to 0, 2. So Rolle's theorem is verified for the given function. Next, this is also very important question for you. Okay. So does fx is equals to mod x satisfy Rolle's theorem conditions on minus 1, 1? Justify your answer. So already you know this is very well known function to all of you. So here mod of fx in mod x is basically nothing but minus x for minus 1 less or equals to x less than 0, and x for x 0 less or equals to x less than 1. So this is the range. So if I plot, if you recall your class 11-12 concept, what is your mod x? Mod x equals to this. Then what is your representation? Sorry, if I can recall, so this is your function. The drawing is not perfect. So this is the figure. Okay, so this is your x-axis, this is your x dash, and this is your y, this is your y dash, this is your origin. and here it is -1, and here it is +1. So this is the rough figure of your function. So from here it is clear that from here it is clear that there is no gap. There is no gap. Okay, there is no gap. My figure is a little bit it's not in perfect nature, but the gap should be equal from both sides. Okay, I try to demonstrate this with some example. Okay, so from it is clear, from the graph it is clear there is no gap, so that means your function is continuous from -1 to +1. Okay, now so f dash 0 at you want to find that your differentiability part at 0, that is 0 point, limit h tends to 0 minus f of 0 plus h minus f0 by h is equals to limit h tends to 0 minus h minus 0 is h is equals to -1. So from the function it is clear, and 0 plus f dash x at x equals to 0, limit h tends to 0 plus f of 0 plus h minus f of 0 by h, limit h tends to 0 plus h minus 0 by h is equals to 1. So from it is clear, from the left derivative and right derivative at x equals to 0 is not same. So that's why fx is not differentiable at x equals to 0. Okay, very simple. And then so here I try to satisfy third condition also. F1 is equals to f minus 1, that is fa is equals to fb is equals to 1. No need to check this. If out of 3, if any one condition is not satisfied, then you can stop the calculation. You can conclude the result. Rolle's theorem is not satisfied. Okay, based on this. But this is the first time you are doing this, so that's why I am trying to check all 3 conditions of Rolle's theorem one by one. So from here it is clear that your second condition of differentiability of the given function is not satisfied. So therefore, the Rolle's theorem is not applicable for the function f of x is equals to mod x. Okay, so this is all about the Rolle's theorem and its application. So this is also another good example. Examine whether the Rolle's theorem is not applicable for the function f x equals to tan x 0 less or equals to x less or equals to pi. So already you know, if I put x equals to pi by 2, because pi by 2 belongs to this region, so your tan pi by 2 is undefined. So therefore the function tan x is not continuous at x equals to pi by 2. No need to check further the differentiability or fa is equals to fb. No need. Already discussed in my last question. Just you have to check whether your function is satisfied or not. If you are from first condition your function is not satisfied, that is first condition is not satisfied by the function, so that means the function f(x) equals to tan x is not continuous at x equals to pi by 2. Hence Rolle's theorem is not applicable to the function f(x) equals to tan x in 0 less or equals to x less or equals to pi. Clear? So this is all about the various different types of question I have discussed in this lecture. Okay, now Lagrange's mean value theorem. Lagrange mean value theorem statement: if fx is a function defined on closed interval AB satisfying the following condition: fx is continuous in open interval closed interval AB and fs is derivable in open interval AB, then there exists at least one value c where a less than c less than b such that fa fb minus fa by b minus a is equals to f dash c. What is the basic difference from Rolle's theorem? Here in Rolle's theorem third condition is not available here. What about the third condition? fa is equals to fb. So from if I put fa is equals to fb to this relation, you can get f dash c is equals to 0, f dash c equals to 0. So from it is clear Rolle's theorem is a special case of Lagrange's mean value theorem. Is a special case of Lagrange's mean value theorem. Now another form, the h theta form of Lagrange mean value. This is also very important form for to solve some important problem. I will discuss later. Let b is equals to a plus h, then any point between a b can be written as a plus theta h, where theta is lies between 0 and 1. Then the above theorem, that is Lagrange mean value theorem, take the following form. If fx is be a function defined on the closed interval a comma a plus h, that is I replace b by a plus h. Okay, satisfying the following condition. Number 1, fx is continuous in a plus h. Fx is derivable in a open interval a comma a plus h. Then there exists a theta where 0 less than theta less than 1, such that if a plus h is equals to f a plus h f dash a plus theta h. This is very important. I can tell you, this is very important. This is very important theorem. You can see, you can solve lots of questions based on this formula. Okay, I will discuss later. Geometrical interpretation of Lagrange mean value theorem. From the geometrical interpretation, from the figure graph ACB, this is a graph of fy is equals to fx. In AB, fb minus fa by b minus a, fb minus fa, that is this is fa, this is fb. This fb minus fa is equals to this one. br b minus a, this is your total a, and this is your b, that is b minus a, that is pq. br minus ar is equals to tan angle ba minus r. The slope of the tangent to the curve y is equals to fx at x equals to c is f dash c is equals to tan theta. So from the Lagrange mean value theorem, we get fb minus fa b minus a is equals to f dash c. That means tan of bar is equals to tan theta. So from here it is clear that the tangent to the curve y is equals to fx at x equals to c is parallel to AB. This your tangent is parallel to AB. Is parallel to AB. Okay. Is parallel to AB. But in case of Rolle's theorem, your tangent is parallel to x-axis. So here your tangent is not parallel to x-axis. Just you can generalize it. Now try to understand with some example. Verify Lagrange's mean value theorem for fx equals to x square plus 3x plus 2 in 1 less or equals to x less or equals to 2. Find the value c if the theorem is applicable. This is also very important question for you. So here fx is continuous because it's a polynomial function, or you know polynomial function is So fx is continuous in closed interval 1 comma 2. F dash x is equals to 2x minus 3 if you differentiate this. So exists in open interval a comma b. So from here it is clear, Lagrange's theorem, Lagrange mean value theorem is applicable because both the conditions are satisfied by the function fx equals to x square plus 3x plus 2 in 1 less or equals to 2. Okay, then there exists, according to the Lagrange mean value theorem, then there exists a point c in 1 comma 2 such that fb minus fa by b minus a is equals to f dash c. What is f2 minus f1 by 2 minus 1 is equals to f dash c. What is f2? If you substitute here, f2 is equals to 4 plus 6 plus 2, 4 plus 6 plus 2, 12, and f1, that is 1 plus 3 plus 1, that is 6. 12 minus 6 by 1 is equals to f dash c. What is f dash? Substitute here, 2c plus 3, 2c plus 3. After simplification, what you have, that is 6 plus 2c plus 3 is equals to c is equals to 3 by 2. Okay, that is 1.5. So from here it is clear that your 1.5 is lies between this 1 and 2. Okay, so this is all about the Lagrange mean value Rolle's theorem as well as Lagrange mean value theorem, and already I discussed some examples with Rolle's theorem as well as your Lagrange mean value theorem with example at the geometrical university exam point of view. Geometrical interpretation of Rolle's theorem and Lagrange mean value theorems are all very important and with related question. Okay, thank you.